Okay, now we can start. So we're moving into t-tests. So we're going to start simple. So now this is where we're going to get into hypothesis testing. So everything we've done so far has been data screening, pre-data checks, how do I make graphs. And we're going to combine all that together with the actual analysis. So graphs and that other thing, data screening, are still going to be useful. So you're going to get a lot of practice. If you weren't so hot at the data screening part, you're going to get to do it more. I know you're all super excited. Get this face like, oh, joy. But that's the only way you learn is practice. Okay? And so we're kind of backing up a second, but most experiments, when they're simple experiments, have one IV that's usually categorical, so 2 or more levels. And we're doing t-tests, so we're going to do 2 levels. 3 levels is ANOVA, that's the next section. 1 dependent variable, that's either some form of continuous, interval, ratio, or just straight continuous. Okay? And that's because this is parametric stats. If your dv is categorical, that's not parametric, so that's chi-square. Okay? And so what we're going to do is manipulate some sort of independent variable, and that's a experimental task where you have some sort of condition, experimental condition, and a control. Okay? And so that's a t-test. We can also do testing people twice. That's dependent T. Or you can have 2 separate groups, like a low group and a high group. That would be independent T. So we're really getting into, like, what do I do if I have just a very simple experiment with 2 levels? And this is levels. Conditions is with ANOVA, so that's 2 or more variables. So kind of a warning. This isn't in the chapter, but if you have doubly continuous data, so let's say you have one of the examples we did before was with a marker that worked. So we had exam anxiety and exam score. I really wish I had this data for y'all's exam because I think it would be interesting. Anyway, so these are both continuous variables, and I think what we had was kind of a curvilinear effect that as you got more anxious, the scores went down. What people are always tempted to do is to split the data in half. So you can have a low and a high group. Because for some reason people think t-tests are easier than regression. T-tests are just a special type of regression. And that would be considered a median split. Okay? So don't do that. Because what happens is that the person who's here and the person who's here have the same score, but you've put them into 2 separate groups. So it tends to reduce the size of your effect, and it tends to cause a type 2 problem. So you'll miss the differences that are there. Okay? So don't make a continuous variable categorical just to do a t-test. We will get to regression and cover how to handle these with regression type analysis, even with interactions. So we'll do moderation. Like I swear, everybody knows I'm in class. There we go. So don't split a continuous variable. This is the gist of that. Okay. And then a quick reminder, so when we're manipulating the levels of the IV, that's experimental. Okay, so t-tests don't really care if it's experimental or quasi or correlational. Like the statistical analysis is often separate from the type of research approach. And so if it's experimental, you're still doing t-test. If it's not experimental, you're still doing a t-test. So just because you're working with a specific statistic does not make it experimental or quasi or correlational. Okay? So if we're doing 2 naturally occurring categories, it's quasi or correlation. You can call it either one. So between subjects, research designs are often called independent designs, and that's when the people are 2 separate people. So they only get one of the manipulations, or they're only men or only women. And so this is when people are 2 distinct groups. Repeated measures, sometimes called within subjects, or dependent designs. There's 10 names for repeated measures. It's really annoying. Is when people get all the levels. So they're in each of the conditions. And that would be normally wide format, right? So I've got 1 column for each one. Okay. We're going to do everything starting in wide and then move to long. And I'll get into why in a little bit. So for t-test, the match to that is an independent t-test goes with between subjects. So we're comparing 2 means based on separate data sets. So 2 different groups of people. And a dependent t-test, sometimes called a paired t-test, is when people have taken both conditions, so or matched samples. The really tricky thing sometimes is when you get into data sets where you have people matched, but they aren't the same people. Sometimes that's called yoked data, where this participant is tied to this participant for experimental reasons. So we have a data set where we have people created a word set, and then these people got that word set, so they're tied together because the data is matched, not the people. So dependent T can also be used when the data matches, and not necessarily the people are the same. So it's a really usually unique case. It doesn't happen very often. Okay, so when we're working with matched samples. What you guys will be doing, people will have taken something several times. Okay, so as you're reading this chapter, everything is going to be taught as a linear model. And you'll notice we've went from chapter 5 to 9, and we sort of skipped regression, because I think it's probably easier to start with t-tests, so something you're at least vaguely familiar with. I remember it's a thing. So we're going to do everything as a linear model. And we could actually use the LM function that you've used for data screening for all of these designs. I think using the t-test function is a little bit clearer what you're doing because it's in the name of the function. And so just know that t-tests and ANOVAs are just special types of regression. They are regression. They just happen to have categorical predictors instead of continuous predictors. So when we switch to regression, it's not really that new. It's the same math. And that's one reason I really like this book, is because he really focuses on all of these are models plus error. Right? And our model is going to be the mean plus the standard error. And it just happens to be that in this case, the model is always a mean. For regression, the model is a correlation or a beta value. So we could do all of this using the LM function, but we're not, because there are some other functions that make it a little easier to interpret. Okay, so if you read the chapter, he does go over how this is run through LM. And we're just going to do t-test, though. Because I've figured out that you guys don't like multiple ways to do things. Give me the one way. And so when I was recording the video for this chapter, it's you could also do this, but I know you guys don't like that, so just do it this way and you'll be fine. So we're going to start with an independent t-test. It's actually the same data for both examples. We're just going to pretend one time it's independent and pretend another time it's dependent. Okay. So are invisible people mischievous? So we had people who got an invisibility cloak and the other people who didn't get an invisibility cloak. I love these examples. Right. And we measured how mischievous they were during the week. And so this is a between subjects design, right? Because they don't overlap. Two totally different groups of people. So it's independent T just because it's two separate groups. The problem with long format in R is that you got to remember that it's independent or dependent. Right? So wide format's nice because, okay, this is repeated, it's the same people over and over again. But if everything is in long format, you just have to remember. Okay? So that's the only issue, really. So let's not import the data yet. Let's go through this first. Okay. So do a little bit of theory stuff. So this is the rationale for independent T. So we've got cloak versus no cloak. Those are the two levels we're comparing. Right? And we've talked a little bit about null hypotheses. If I have a null, maybe I have a marker that'll write somewhat. I'm going to start with a null. Does anybody have one? Jessica normally has you. Okay. Don't let me steal it. There we go. All right. All the loud noises. All right, so we've got a cloak group and a no cloak group. So if I'm using my mean as a model, what will we expect to have happen? So what is the point of a null? Then nothing happened, right? So they will be equal. Good. So my cloak group and my no cloak group have the same number of DVs, so mischievous X. Is that how you spell it? Good thing this is only recording the screen, right? You can't tell I can't spell. You can in the other videos. It's not a secret. So, is that how you spell it? No, I before E, except after not CH. There we go.
No.
No?
It's UBX.
It's fine. Lover of bad X. So moving on to the research. Same thing. Cloak, no cloak. Now what? Close enough.
The mean for the cloak condition would be
Higher, right. Level? Yes, level. Right, it could be higher, could be lower, could be not equal. Right. We're not going to do one-tailed tests. So I might think that it's going to be higher, because that would make sense, right? If I'm hidden, I'm going to be bad. But since we're doing a two-tailed test, it's always that they're not the same. So we're not predicting one side or another. But some sort of difference, right? I just want you to get the basic gist that the null is no difference, and the research is that there's some difference. And so we might believe it's going to be higher or lower, but we're going to predict something happened. Right? So our experiment worked, and people are different. Right? And I had something else. Right? Yes, it's on the next slide. So I'm going somewhere with this. So we took 2 samples, and we're going to calculate the means. So we're going to use t-apply to calculate these means and see if it looks like something happened. So now we're going to load the data set. All right. So let me get the studio here. So let me close up one. All right. I have the data hidden somewhere. Nope. Okay, now this should work. Yeah. All right, so I've got my data, and it's in long format. Oh, and it has the stupid I thing. Oh. Okay, so let me fix that problem real quick. So remember, you can do call names of the data set with a square bracket for 1 for column number 1. All right, and I'm going to change that to cloak here. So all I did was fix the weird symbol problem. All right, so to calculate means and descriptive stats, what we need to do is make this whole thing bigger so you can see it. There we go. I can use that t-apply function. We're going to use t-apply a lot. So if you haven't quite got the hang of t-apply, practice. Okay. So the first column has to be, or the first piece of information is the dependent variable. Okay. And there are so many functions that it's y comma x, okay, or y tilde x. So if you aren't sure, go with y first. Okay. So our mischief variable is first, okay, comma, and then the variable you're going to split on. So that second variable needs to be a factor variable. So I'm going to split on cloak, calculate the mean. Okay. And don't forget, if you have missing data, I don't in this data set, you can also add NARM equals true to deal with the missing data. So if you're doing skew and kurtosis, you could have added that in there as well. So I'm going to calculate my means, and let's look at them. So we've got a mean for our cloak group of 5 bad actions, since I can't spell. And our no cloak group is 3.75. So that looks like you were going right, that our cloak group is higher than our no cloak group. But is that statistically significant? So the point of a t-test is to get at, is that a big enough difference to consider that practically, or not practically, that's effect size, statistically significant. The other thing I'm going to do is calculate my standard deviations. So I got 165 and 192. And then now I'll have these to do my write-up. Yeah?
Sorry, I'm doing something wrong. It just tells, it won't run for me, and it says arguments must have the same length.
Oh, that's a stupid error. Okay, so one thing is you spell cloak with a lowercase. messages are not always the most helpful. Right. Okay, anybody else? Within the means? I actually was looking at a website earlier that was like interpreting our error messages, and that was one of their first ones they had. Was arguments are not the same length. It's because you've usually misspelled the variable name. And sometimes it actually is that they're different lengths, but not all the time.
I wish there was like some website where you just translate all your error messages into like what it really is.
Yes, agree. The problem with that is it sometimes depends on which function you're using. So in tapply, that means the names are spelled wrong, but in cbind, that literally means they're different links. So, yeah.
Sorry, I'm getting the same message as.
Oh, you're fine.
Okay. Can you drop down the long video for me? I gotta fix that weird fucking stuff. I don't think it's stuck. Yeah.
Okay. Other people? What? Why?
Oh, is that? Stick it. Oh, don't run this line. That resets it. Some down here to me. Yeah.
Okay. Where was I at now? Okay, we calculated the means, standard deviations. Right. So I just stuck them in here so you can see them again. Yay! All right. Oh, this is a fancy slide. Get excited. It's kind of goofy example. Okay, so this is a totally different example, but it's the idea of what is the point of an experiment. So we've manipulated if they got a cloak or no cloak. This example is I have one group that gets a lecture with a professor, and the other group gets a lecture with no brains. So we're giving the professor a lobotomy, and we're going to see what happens. And we're measuring how well they've lectured. And so we've got participants who either like their lecturing skills or don't. And so we're going to get into like what is the point of like how does the statistic actually work? So we have variance created by our manipulation. So that's good variance. So good variance. Oh, not God. Good. So that is created by us. Okay, our manipulation or IV. It's good variance because that's the number you want to be really large. So you want the differences between groups to be large because you made it that way. So the difference between 5 and 375 here is because of the cloak manipulation. Or we hope, anyway. So the removal of the brain is sometimes called systematic variance. So good variance is also systematic. And we've used systematic before. And then we also have variance created by other things. This is bad variance or unsystematic. Specifically in this numerator-denominator format. And so that's created by unknown factors. Okay. So there's differences in ability, time of day. These are all those nuisance or confound variables. Often just called error. So error for whatever reason. Maybe because they figured out what the experiment was about, maybe because they thought it was funny, like things that aren't because of what we manipulated. So it might be that we have some people in the cloak group who are just naturally more mischievous, or maybe there's some people in the no cloak group who are very good all the time. Right. So if those two samples, so cloak and no cloak, come from the same population, this is all the theory stuff, we would expect their means to be equal. So that's what you guys told me the null was. Okay? And so if I ask you what would you expect the means to be, it would be that they're equal. Okay? So maybe the means differ a little bit by chance. So they're not perfectly the same. 5 and 375 are not literally the same number. But if the null is false, right, so if this no difference is false, then we would expect large differences to happen, but very infrequently. Okay? And so this is the real rationale of null hypothesis testing. We expect everything to be equal, and if they're not equal, that probability of them not being equal needs to be really small. So null hypothesis testing is a little odd because this is, I think I explained this as Rock'em Stock'em robots before, where we're testing this idea. So we're either getting the null is true or the null is false. If the null is false, we say the research is supported. So we never actually test the research hypothesis. We just sort of rule everything else out. So it's like the Sherlock Holmes, right? So we're ruling out that this is true, so this must be true. It's kind of like policing too, where the defense tries to put up, well, maybe this person did it, and they're like, nope, here's all the evidence, this person didn't do it, so we're back to you're the guilty party. So our legal system works in the same way, which is a little frightening. So they also try to prove the research is true, but they also have to knock down all the other theories that the defense will put up. So we're going to compare the difference between sample means that we collected, so 5 minus 3.5, to what we would expect if there were no effect. So I'm going to compare the mean cloak versus the mean no cloak, so that's 1.25 points different. If the null was true and they were equal, what would the mean difference be? That should be very easy. Okay, if the groups are equal and you subtract them, what do you get? 0. So when you get to the homework, don't overthink that question. Okay. So if there's no difference between the means, the difference will be 0. So we're going to compare 1.25, which is what the literal difference is in this study, to a difference of 0. Okay. And we want, obviously, our difference to be larger than 0. Okay. Has to be value-wise. But we can't literally just subtract them and say, okay, 1.25 is now 0. So we have to compare it to something. So we've got to have a gauge for it. So this part's the model. We're using the mean difference as our model. So mean 1 minus mean 2. And then we also have to kind of deal with the error. So our error is the estimate of back variance. Okay. So if the mean difference has a larger ratio than the error. So if the difference between the two samples is bigger than what we would expect based on chances, so 0, and then also controlling for our unknown factors, so standard error. What does it even say? I'm not sure. We can assume one of two something. I don't know where that slide is going. But basically, if the difference between samples, 1.25, is larger than what we would expect based on standard error, period. Okay. So how does all that work with t? Okay. So if there's no effect and our sample means fluctuate a lot, then basically these two samples are typical from where they came. So they're the same population. They're not different. Okay. If the two samples are different, they're going to come from different populations. So basically we're testing if the cloak group and the no cloak group are the same, so the same population, or if they're different populations. Okay. We still want them to be representative of their populations, right? Because you always want your sample to represent your population. Otherwise, you're testing a screwy sample and it's not going to replicate. Okay. But if they're two different populations, we'll get a significant test. Okay. And so then the null would be false. So essentially what we're testing is if they're equal. If they're equal, they're the same population, therefore the means are the same. If they're not equal, we're going to support the research. They're different means, different populations. And kind of ish. And that is actually the basic gist for all the tests we're going to do. Testing if things come from the same population or a population where things are not related to a population where things are related and they're different. Okay. So as the mean difference gets bigger, we're more likely to believe that they're different groups. Okay, and the means are different. So the larger the difference, if it was 10 to 3.75, that's quite a big difference. But the real problem is the scaling. So on a 1 to 5 scale, a 1 point difference is really large. But on a 1 to 100 scale, 1 point difference is kind of small. So we have to have something to judge that against. We can't use just the difference between means. Right? And so that's why we use the standard error to judge, is this a large difference or a small difference? Okay. So if, yeah, we covered this. So getting into t. So the way that t is calculated for both tests with small mathematical differences is the difference between means minus the expected difference between population means. So we've got difference between means, 1.25, minus what we would expect if the null is true, which you guys figured out was 0, divided by some form of standard error. And the standard error depends on which test we're talking about. Okay, so we'll get into the actual math here in a second. But essentially, it's a 1.25 difference compared to the variance in that group, those groups together. And so this is the way we create a ratio. So what is T? I get this question a lot in my undergrad class too. Like, I don't know what to do with the number. What is this thing? T is just a ratio of good variance to bad variance. And so if you like sports betting, it would have been a bad weekend for you. Because, well, what a bunch of hot mess games. But if you've ever looked at odds ratios, what are the odds of me winning this test or winning money on these bets? Or if you like to gamble, what are the odds of winning this game? T is just odds. So the odds of the good variance being bigger than the bad variance. So the odds of the null being false. So you want big numbers. The larger the ratio, the more the odds are in your favor, to make a bad Hunger Games joke. Okay. And so you want the mean difference to be much larger than the error. And we've talked previously about error being the way we judge if a model is good. So if the error is small and the mean difference is large, you're getting a big difference between means. All right. So this is the scary math, though. So here's the way independent T actually works. And pooled variance is just quite unfortunate. What happens is you get mean minus mean. So that's the numerator here. So I'm just subtracting mean 1 minus mean 2. It does not matter which order they go in. Because we're going to do a two-tailed test, and we don't have to care about the order. Okay? And so that's why it's important to have the means. Because if I subtract cloak minus no cloak, it's a positive number. If I do it the other way, it's a negative number. So when you get the T value and you're like, okay, it's negative, what does that mean? Go back and look at the actual numbers. Okay, so cloak is higher, it's got a bigger number. So subtracting mean minus mean. And there's an implied out here minus 0. Okay, but we don't have to literally write that because it's always 0. So minus the null expected value, which is 0. Okay. Divided by standard error. So this is a two-part formula for standard error. And why is it so crazy? Well, now we have two groups. Let me see if I can draw this. We have cloak. A no cloak. Okay. So I've got the mean for 1 and the variance. Okay. It's like 2 hours a day that I'm in class, and that's when everybody calls me. Okay, so I got my mean and my variance. Okay. And what we've been doing is talking about, here's the mean for this group, here's the variance, is which one has the best model. But I can't just add them together on the bottom. And so what all of this crazy math does is it creates an average variance. Okay, so it's an average standard error, essentially. And so it allows us to have the T distribution. Okay. So the T distribution is a distribution of mean differences. So its score is mean minus mean in the middle. Okay. So both of them feeding into it. Does that make sense? So we're creating a distribution of subtracting these two from each other. So mean minus mean, which means the average score for T is 0, because the null is true, m minus m is 0. But to calculate the variance of T, now I have to do something. And I've got two variances. And I don't want to just subtract them. That doesn't make sense. Because if the variance is 0, you got problems. Okay. So I need to come up with some way to calculate the variance of T. And that's what all that grossness is. Okay. So in this chart, S here is just standard deviation. S squared is variance. So it's the variance of each group times their degrees of freedom. Okay? So here's n minus 1. So each group's variance times their degrees of freedom. Okay? And then divided by the total degrees of freedom. So if you remember the formula for averaging things, is right, add them up, divide by n. Okay? So variance for each group times the number of people divided by the number of people. So this creates a weighted variance. It's called pooled variance. I hate that term because it doesn't, like pooled, it just, I don't know, it's a funny word to say and it sounds funny. So it should really be weighted variance. Okay. It's not quite an average because we're not dividing by n, we're dividing by degrees of freedom, but it's close. So it's a weighted variance. So if one group has more people than the other, then it weights it towards the people that you know more about. Okay, so it will bias it towards the sample with larger numbers of people because those variances are better estimated because it's closer to the population. Okay, so it's a weighted variance. Okay. If you have the same number of people in each group, it is literally an average. Okay. If you have different numbers of people in each group, it's biased towards the larger group. Okay. So that's pooled variance. You take pooled variance and divide it by n. So remember the formula for standard error is variance, right? No, I'm sorry. Standard deviation divided by square root of n. I know it's been several weeks, but SE is SE over n. Okay. And that's what each one of these is. So this is variance. So if I took the square root here, it would be standard deviation divided by n plus standard deviation divided by n. So then we add the two standard errors together. Okay. So you create a weighted variance, and then you take the variance from 1 and 1, 2, and add them together. Only you don't do that by hand because math. Okay. I don't even make my baby stats class do that by hand, but I think understanding that it's a weighted error is the important part. Okay. Because you can't just add them together, that doesn't work. Okay. And so make sure you understand, okay, so I got degrees of freedom, where is that here? That's here. So I got n minus 1 for each group, so n minus 1, n minus 1. And then total degrees of freedom, which is n minus 1 plus n minus 1, or n minus 2. Okay. So it is still n minus 1. Degrees of freedom isn't changing. It's just we have two groups. So n minus 1 plus n minus 1. Add them together. Standard deviation is the pooled variance part. Standard error is when I divide by n. Okay. So these are not new concepts. They're just weighted now. Okay. So if I calculate all that out, I will get a t-value. Oh, did I upload that table? I hope I did. Okay. So let's say our t-value, if I did all the math, which I've actually done already, so I can figure out real quick. So t-value is 1.71, because I don't want to do the math by hand. Right? What does that mean? Okay. So we've said the null is here, where mean minus mean is 0. Okay. That's on average what happens. Our t-value is 1.71. Okay. So this is us, our experiment, which I always draw as little people in my example. This is a sample. So what does that number mean? Well, it's a ratio of good variance to bad variance. So it's 1.25 over the standard error, the weighted standard error. Okay. But how do I know what that number means? Okay. And so we're going to use a t-table, and I'm going to tell you now why you should care, and then later when we come back to it, you'll be like, oh, God, I forgot about that. Okay, so why should we care how a t-table works? Well, generally you'll get p-values, and we'll talk about how to interpret those in a second. But when we get to ANOVA, a lot of the type 1 error corrections require you to use a table. So we're going to kind of cover tables right now. And then when we get to these, we're going to come back to it. Okay, so we won't do this just a whole lot until a couple weeks from now. So, t-table. Did I upload it? Good question. Someone might be able to tell me if I did or not. I feel like I did. Maybe I didn't link it. Because the computer guy was talking to me at the same time, and I was like, I'm trying to do these grades so they don't kill us. There it is. Okay, good. So if you refresh the notes page, you will find yourself a T-table that is copied from my undergrad stats book, because it's the easiest table I've ever found to read. So this is the simple T distribution. We're always going to use this two-tailed psi, because we're never going to do a one-tailed test, because most people consider that cheating. Right? So only two-tailed over here. I'm going to use alpha as 0.05. And so that's type 1 error correction, p less than 0.05. So we're getting into hypothesis testing, so it's not 001. So pretty much always this column. Now my degrees of freedom. So how many people do I have, and how do I calculate that? So let me look at the data set. So I'm going to calculate that same t-apply function with length. Okay, or you can use the table function, or you can use the summary function, but I know you guys don't like this, so we're going to do length. Because we did that before. So there are 12 people in each group. So remember the length function, we used it to calculate standard error in chapter 2. It will also tell you how many people are in each group. Okay? So then you can also do degrees of freedom. Okay, so n minus 1 for each group. So it's 11 plus 11. Okay, so what is 11 plus 11? Easy question. 22. So like panic, math. Okay, so 22 is our degrees of freedom. Because we have 1 degree of freedom for each group, but for the test we need 1 number. So we add them together. Okay, and that's where the n minus 2 thing comes in. Okay. It does, oh yeah, it does in the test part as well, yeah. But let's say you just had t, and you had to figure out, is this significant or not, is what we're kind of doing. All right, so 22, I'm going to go over here to 22. This is degrees of freedom column. It's 2.07. Bless you. So 0.05 down to 22, so 2.07. Kirby, your markers die. It's okay. I'll go get one here in a second. Let me take a break. Okay. So that means, to give you guys the example I always use in my undergraduate class, which sometimes goes well, let's say you have a VW bus, because that's all I can draw. Okay. And so you're in the what is the name of the car in Scooby? The Mystery Machine, yes. Right? And so you're trying to get away from the null being true. So if the null is true, the mean difference is 0 and nothing happened, your experiment was a bust and you're sad. And so you're trying to get your little race car or your mystery machine across the finish line. Well, the finish line is 207 because we had 24 people in the study, so minus degree of freedom for group 1 and group 2. So you got 22 degrees of freedom. So the bad thing about T is that the cutoff score changes every single time, just like Mahalanobis. So it's not 1.96 all the time. So I'm trying to get across the finish line here. We only made it to 171 before we ran out of gas, so it's not significant. So basically this area between these 2 points is where you would say the null is likely. Okay. The research was not supported. There really isn't a difference between these 2 groups in this experiment. If I had gotten past my finish line, I would say the null is unlikely, so the research is supported. And so essentially, null hypothesis testing comes down to little mini race cars with lines in the sand. And if you don't cross the finish line, the 0.05 finish line, you don't support the research. If you do cross the finish line, you do support the research by rejecting the null. Weird terms. Okay. So when people are talking about things being statistically significant, they're talking about the mystery machine crossing the finish line. You won't forget it that way. Or you'll be like, at least she gave us a weird example, something about something. Okay. So that's how I can use a table. So I can tell you without knowing my actual p-value that this is non-significant. Okay. But, before I get into that, APA, the 5th and the 6th edition, I believe, talk about using exact P. So let me give you, back up 2 steps. So we're going to use alpha as 0.05. So our type 1 error cutoff is 0.05. And that's where people are talking about P less than 0.05. And it's significant. Yeah, your life is happy. But what you actually calculate in this study is an exact P. It should be called P found, P experiment, or P something. That sounds terrible. But anyway, you can laugh about it later. So what we're going to do is find the p-value for just this experiment. So that tells me how likely were these 2 groups to happen given this ratio of mean difference to error. Okay, some people say by chance. So how likely is the null given these 2 ratios? Right, so different scores over standard error. And so we want that to be really small. And that's what confuses a lot of people at first, is that you want your probability to be low. So, because you're talking about the probability of the null, not the probability of the research. Remember, we never test the research. We're always testing the null. So I run a really small p-value. If p is less than 0.05, you would say it's significant. If it's greater than 0.05, it's not significant. But no matter what, when you're writing these out in APA style, you do p equals and list the number. Okay? And less the number gives you is really, really small. Don't ever put p equals 0, 0, 0. I will murder you. Not literally. This is being recorded. So not literally. But I will count you will be wrong. Okay? So probabilities don't equal 0. They can be very tiny, but they're not 0. Okay? And so we'll do less than 0.001 or something. I have an example. We'll get to that. Okay? So when we do tests like this, we want to get exact p, so p found for this experiment. But when we get into type 1 error corrections, we might have to do sort of inexact p. It's less than the new cutoff, which means it's less than 0.05, but you can't calculate it exactly. Okay. All right. So let's do this slide, and then we'll take a break. So all of that data screening stuff that you guys love still applies. So that's why there's a video on YouTube already up today of data screening for T. We're not going to do it in class. And so we can do the multivariate rules and still get the same basic, what's the word I'm looking for here, results as the univariate rules, except in 1 or 2 little cases. And I go over that in the video some more. So I always do this multivariate unless it just literally will not let me run it, or if I have problems, okay, because it gives you the same basic answer. Okay? And then I have that all laid out in a video of like, if this error happens to you, try it this way, that sort of thing. Okay? So before we get into how do I run this in R, let's take a quick brain break, and I'm going to get some more markers. So.